Hello, everybody. Sorry for not being present in person for this summit. Last minute issues with my travel plan have forced me to present this in absentia. Modern day architectures boast of supporting instruction extensions, IEs for short, in order to execute well defined macro operations efficiently. However, these IEs need to be defined prior to spinning the chip. In this work, we provide an architectural extension to redefine a massively parallel architecture to support IEs that are defined post silicon. This work was carried out at Morphing Machines in collaboration with CAD Lab, Indian Institute of Science, both based in Bangalore, India. This slide shows the key team members who contributed to this work.
So, what is the problem we are trying to address? Instruction set architecture, ISA for short, is a contract between software and hardware to speak the same language. Once the processor supporting an ISA is produced, the set of instructions cannot be extended by new instructions. Having said this, modern architectures do support extensions to instructions, that is IEs. However, these IEs are defined pre-silicon. It is our endeavor to step into the land of forbidden, that is, to support IEs post-silicon.
We take Redefine, the massively parallel processor, the flagship architecture from Morphing Machines, as the base architecture, and show how we extend the ISA of Redefine post-silicon by a runtime reconfigurable data path. Redefine adopts dynamic data flow execution paradigm. Redefine's runtime supports creation of flexible regions of compute and memory resources. This helps in spatial and temporal sharing of resources and supports parallelism with varying granularities. Redefine has a multitude of compute resources interconnected by high-speed network on chip. Compute resources comprising multiple compute elements exploit instruction-level parallelism. Each compute element supports a subset of RISC-V ISA. An important feature of a compute element is to expose a set of well-defined interfaces so that a user is given the ability to plug in hardware of choice. This is the feature of Redefine that enables support for post-silicon IEs. This picture shows a 264 compute element Redefine. As you can see, the network on chip, which is in a bidirectional toroidal mesh topology, connects the compute resources of Redefine. Packet switch network on chip aids in easy scalability of the Redefine execution fabric. As mentioned earlier, Redefine has a multitude of compute resources interconnected by high-speed network on chip. Each compute resource houses a number of compute elements. Using the metadata generated by the compiler, the orchestrator housed in each compute resource manages execution of kernels. Redefine's internal memory, depicted by DSM in the figure, is distributed among all the compute resources. The Redefine compiler generates optimized Redefine executable kernels from source code written in standard sequential programming languages. Currently, the C language front-end is supported. The Redefine compiler exposes task-level parallelism by compiling kernels to multiple hyperops and instruction-level parallelism by further breaking hyperops to p-hyperops. Orchestrator, using the metadata produced by the compiler, exploits these parallelisms by distributing hyperops to multiple computing resources and p hyperops to multiple compute elements. The redefine compiler emits redefine executable format of the code written in a high level language using the RISC-V instruction set extended by redefine specific instructions. Redefine can be customized for a domain of applications. This is enabled by the ability given to the user to supplement hardware of his choice to compute elements. This figure depicts a custom function unit, CFU, that is plugged into each compute element of Redefine using the well-defined interfaces provided by Redefine. If we have the objective of supporting post-silicon IEs, we necessarily have to have the ability to compose CFUs on demand. In order to support arbitrary post-silicon IEs, we need to think in terms of generic reconfigurable hardware. Let us call this unit as PoSiCore, a short term for post-silicon core, which supports post-silicon IEs. It is important to note that post-silicon IEs follow the same execution semantics as pre-silicon IEs. Redefine, as you might have noticed, is suitable to support multiple domains of applications. Hence, use of PoSiCores as add-on hardware in Redefine provides composable CFUs for multiple domains. It is important to note that PoSiCores also exploit both temporal and spatial parallelism. This slide summarizes the role of PoSiCores in Redefine. PoSiCores are integrated with the Redefine architectural framework. The data paths, as mentioned earlier, are configured at runtime, and they are configured for runtime for user or compiler generated or identified IEs. The PoSiCores enact the role of custom hardware to support heterogeneous islands of domain or application specific IEs. A pictorial depiction of a compute resource of Redefine with a PoSiCore integrated into one of the compute elements is shown in this figure. Very similar to the way a CFU is integrated into a compute element, a PoSiCore is integrated using the well-defined interfaces provided by Redefine. The three main components of PoSiCore are the fetch decode unit, FDU, the load store unit, LSU, and the configurable custom function unit, CFU. The fetch decode unit fetches the instructions from DSM and decodes them. Appropriate control signals are generated which control the rest of the modules of PoSiCore. The load store unit of PoSiCore is responsible for data movement between memory, CCFU, and CE. It has a vector register file, a shared address and data register file to facilitate streamlined movement of data across the pipeline. The configurable custom function unit consists of regularly laid out compute units interconnected by switches. A compute unit is connected to 4 of its neighboring switches, and each switch is connected to 4 neighboring switches. Each compute unit is capable of performing arithmetic and floating point operations.
An IE for which the data path needs to be realized on this unit is represented as an acyclic data flow graph, which is shown by the red lines in the figure. This graph is overlaid on the CCFU to realize the desired data path. This composition is effected by configuring the CUs to perform the desired operations and switches to consume input data from sources and supply output data to destinations. All peripheral switches can be used to transfer inputs and outputs. FIFOs that exist between switches in the function unit ensure that stale inputs are not consumed by the CUs and outputs produced by the CUs are not overwritten. The task of configuring the CCFU is the responsibility of the CE to which it is attached. Once the resources are composed as per requirement, this unit can be repeatedly used to perform the desired function over different sets of input data. The CE sends the configuration information using switches at the southern port of this unit. This figure shows CCFU configured to perform different IEs. The first one shows the sum of absolute differences as an IE is realized on the CCFU. The same CCFU is then configured to perform another IE, namely the inner product of two vectors. Yet another example of an IE that is realized on the CCFU is the radix 4 FFT operation.
It is evident that the NRE costs are saved due to the support provided by the hardware platform in terms of PoSiCore. PoSiCores can support multiple applications from different domains. Performance obtained by runtime customization of PoSiCore is expected to be close to those of handcrafted custom function units, and the power expended by PoSiCores are expected to be close to the power expended by handcrafted hardware. REDEFINE, a multiprocessor with PoSiCores implanted in CEs, provides a platform for carving out heterogeneous islands of domain or application-specific IEs. Thank you all for bearing with my absence.